in the field of C++, there's nothing else. This is the very top of the C++ conferences. Here you will find the newest stuff. It's huge. You can meet all the experts. And the community here is nice. You get to network with the very best people.
Are in the correct room. So welcome to our session on building secure C++ applications, a practical end-to-end approach. Let's start with brief inputs. I'm Chandranath. I'm a developer at Microsoft. I've been in the Microsoft Edge browser team since 2018. I've been programming C++ on and off for more than 20 years. This is my first time attending CppCon, so I'm really excited to be here. With me is Bharat.
Hi, I'm Bharat, and I've been with Microsoft Edge browser security team since 2018. And I've been working with C++ for almost a decade, on and off, and I'm glad to be here.
Okay, before we move on, a quick note on the questions. We kindly ask you more questions until the end of the presentation. If the question relates to a specific slide, please note this number so that we can refer to it during the question and answer. Okay, moving on. Why this talk? So we all know that C++ is a powerful language, but it's also memory unsafe and has a wide range of undefined behaviors. Now, we can't simply rewrite the massive amount of existing C++ code into a memory-safe language overnight. Microsoft Edge, the browser that we work on, is built on Chromium, which is predominantly C++. So we are in this boat. Fortunately, we can make significant progress without a full rewrite. So Herb Schutter wrote this blog post in 2024, where he laid out a practical approach towards C++ safety. He laid out 4 key safety categories: bounds, lifetime, initialization, and type. And he also mentioned that he believes a 98% reduction across those 4 categories is achievable in new or updated C++ code and partially in existing code. So our approach has the same spirit. We totally understand that there is no silver bullet. We chip away at the problem to make it incrementally better, including moving some portions to memory-safe language like Rust. So in this session, we'll walk through our approach in Microsoft Edge. We'll walk through how our Edge team tackles safety across core safety categories: bounds, lifetime, initialization, and type. And we'll also touch upon a little bit on thread safety, definition safety, reducing other undefined behaviors. Note, this talk focuses on safety to minimize exploitable behavior. Now, we all know that safe code is not equals to correct code, right? So we'll also touch upon some strategies we use to improve overall code correctness. So now safety is critical across the entire development lifecycle. So we'll expose safety categories, safety practices across each of these phases: design, implementation, code review, CI pipeline, and after release. Obviously, we'll focus a little more on the implementation portion. Now, many of the techniques we'll discuss were developed by the incredible open source community at Chromium, so we're really excited to share this with you. A quick note on our C++ environment. So our project uses C++ 20 with Clang and Libc++. Exception handling is disabled. So our discussions today will focus on the behavior of this specific toolchain, not on other compilers like GCC or MSBC. Okay, let's start off with the design phase. Let me hand it over to Bharat.
Thanks, Chandra. So let's start with the design phase. Our security begins at design phase. And to understand our process, let's look at our architecture. We have the same architecture as Chromium, where we have the multi-process model. Our browser process is the most privileged because it runs at medium integrity level on Windows. And then we have the render processes, which are untrusted because they're least privileged and they run as untrusted IL on Windows. We also use Mojo for the inter-process communication. And by default, we have a stance that render processes are always compromised. And if render process needs to perform any privileged operations, we use the Mojo message to broker that to the browser process. We also follow the Chromium's rule of 2. What that rule is, if you have a code which processes untrustworthy inputs, and the code is written in an unsafe language like C, C++, and your code needs to run in a process with either no sandbox or a high privileged process like browser, all 3 should not be true. What that means is, like, if you want to parse JSON in C++ in browser process, that's a big no-no. You can do the same thing in a utility process which is sandboxed, or you can use the Rust language for this same. How our security review process looks like: we have the security champions along with our security team. We review the design of every feature that comes our way. And here are the things that we look for. Are we introducing any new entry points for the untrusted input? And if yes, do we need any new processes to handle that data? Or are there any new inter-process communications, Mojo communications required for this feature? And are there any new additional fuzzing coverage that will be needed for this particular feature? With that, handing over to Chandra for bound safety.
Thank you, Bharat. So let's look at bound safety. So this will be, this section will cover the spatial memory safety category. So we'll focus on two things. One is Libc++ with hardening, and the other is unsafe buffer usage. Let's look at Libc++ with hardening. So Libc++ offers 4 hardening modes. One is unchecked, where there's no hardening. There's a fast mode, which is enables essential and low-cost security checks. So this is recommended for most production builds. There is also an extensive mode, which does whatever fast mode does, plus adds some additional ones with non-moderate overhead. And finally, there's a debug mode, which actually has a lot of checks, but is not supposed to be used in the release production because it has a significant overhead. Okay, so what is the compiler option to use? So there is just a flag. There are 4 values of this particular flag, Libc++ hardening mode, and each of these turns on one particular mode. So there are multiple categories over here, as you can see. Fast actually covers only 2 of those categories, valid element access and then valid input range. Extensive does a lot more, and debug actually does everything of those. For our project, we use this one, the extensive mode. If we quickly look at the categories, you will notice that Libc++ hardening handles more than just bound safety. So we're just covering bound safety over here, but it handles a lot more than that. Okay, a quick note on C++ standard library hardening. So C++26 adds supports for standard library hardening. Herb Shutter actually highlighted this as a part of his keynote in C++ on C this year. Now, Libc++ offers more comprehensive hardening than what is currently proposed for C++26. So now we say that we are actually doing hardening Libc++. What happens when an hardening failure occurs, right? And that can actually be configured. So we can configure the hardening failure. How do we configure that? We can configure this with a particular macro. And for our code, we are just configuring that with a built-in trap. So what is a built-in trap? So it causes the program to stop its execution abnormally. It triggers an immediate CPU trap, causing an immediate and unconditional crash. On x86 platform, mostly it's implemented with a UD2, which is an undefined instruction. Now, this ensures that the program halts immediately without giving an attacker a chance to manipulate the program state. So when you see me mentioning traps in the later slide, so I'm referring to this non-exploitable crash caused by built-in trap. With that, let's look at the first category. Some examples of this one, valid element access. So let's look at what the standard says. It checks that any attempts to access a container element, whether through the container object or through an iterator, are valid and do not attempt to go out of bounds or otherwise access a non-existent element. Let's look at some code. So vector is a class which has this. For the subscript operator, if it's called with out of bounds, if front, back, and pop back are called on an empty vector, or if an erase is called with an end, all of this will trap. So here is some code. We have a problem vector, which is an empty vector, and we are calling front, back, and pop back with an empty vector. This will trap. If you call out of bound index out of range, then that will trap too. And finally, if you call erase with a v end, this will trap too. If you don't have hardening on, then this call will just maybe crash at runtime. Similar to vector, there is also string, which actually hardens all these particular functions, the subscript operator, front, back, pop back, and also with erase. So here is a similar code called with an empty string. So front, back, pop back, called on the empty string, they will actually trap. And then when index is called out of range, that will trap too. And finally, when erase is called with end, that will trap also. Now, what is interesting over here is that if this code is built and run without hardening, it doesn't actually crash and it produces this particular output. So hence the undefined behavior, and hence we need hardening. Okay, one more type to consider, optional. This one, if it's called with the arrow operator option is called, or the star is called on it, when it's empty, then this will trap too. Here is some code that does that same thing. Note, optional is actually not a container, but it still comes under this particular ambit of this particular category. Here also, if you don't have hardening, then this code doesn't crash at all and prints that particular output. Similar to optional, expected is a similar kind of a type, and that is also covered in this ambit. And in this case, the similar operators are covered. So arrow operator and the star operator, when expected has no success object, if you call that will trap. And if you call error function, when expected has no error object, that will trap too. Some other containers that are covered: string, string view, span, array, list, and deck. Obviously, this is not an exhaustive list. Now, what is interesting is that it does a little more. So it actually goes beyond containers, like algorithm. So if this min, max, and min, max are called on an empty range, like this, see here we are calling min, max, and min, max on an empty range. So all these calls will actually trap at runtime. Okay, we end our exploration of valid access element. Let's look at the next category, which is valid input range. So what does the documentation say? So checks that the range is given as input to the library are valid. The sentinel is reachable from begin iterator. So let's see an example. Vector. So if you call erase of a vector with fast greater than equals to last, what I mean by that is like this code. So you're calling erase with a vector with end and begin instead of begin and end, right? So this will trap. Now, if this is built without hardening, then this code there is no crash and everything was fine. Similar to vector, a string is also like that. If you call erase with fast greater than last, like erase being called with end and then begin instead of begin end, that will trap too. And in this case also, if you call this, if you compile this code without hardening, there is no crash. We'll cover a final category for Libc purposes hardening before moving on, which is non-null. So this has nothing to do with bound safety, right? So this is documentation. This checks that the pointer being dereferenced is not null. And it mentions that null pointer dereference would not compromise memory safety on most systems. However, it's an undefined behavior that can result in strange errors due to compiler optimizations. And we'll see one such issue later in our slides. Just quickly mentioning some of the things that are covered. So string has multiple functions that actually take const caster, and all of those are covered. I'm just showing examples of two constructors over here, string view, sorry. And then, yeah, if you call it at runtime with null pointers, this will all trap. Similar to string view, there is also string. I'm showing two functions of string. There are other functions also. And if they're called at runtime with null pointer, they will trap too. So it brings us to the end of our Libc++ hardening section with the question, is more bound safety necessary, or does this provide all that we need? Let's see an example. So this is a print function, which just takes an int star array and a length, and it just tries to print out something, right? Seems harmless. Code compiles. Here's the output. As you can see, something is wrong, right? And you immediately notice the programming error. So instead of I less than length, I used I less than equal to length, right? Which is out of bound access, undefined behavior. So this code may crash at runtime with sanitized builds. However, most production builds are not sanitized, so this can lead to exploitation. So this is where the Unsafe-buffer-usage comes into play. It attempts to convert such code construct to compile time error. So it's actually just a compile time flag. Let's look at it. So this was the code that we had, which compiled fine and then ran into errors at runtime, right? So the moment we compile this with Unsafe-buffer-usage, this fails to compile. And this is what's printed. So the point to note over here is that the actual failure was I less than equal to length. That is the condition that was failing, right? But that exact error location is not pointed out. It just points out coding patterns which may cause problems at compile time. Okay? The coding patterns that can problem at runtime are pointed out. So let's try to understand something a little bit better. So here is some code over here which just actually does the right thing. And this also gives the same error, right? And as you said, this code is fine, but it's the pattern that is pointed out over here. So LLVM safe buffer documentation contains a lot more information. I'm just pulling a little few points from that link. So it says that buffer operations should never be performed over raw pointers. So the warnings are actually emitted for array indexing with subscript operator, doing pointer arithmetic, or actually calling bounds unsafe standard C functions like memcopy, memset, etc. And it also gives a sound advice. It says that all buffers need to be encapsulated in safe containers and view types. Safe containers being array, vector, string, and view types being span and string view. So let's take this first one, and let's look at these particular examples with the array indexing with subscript operator. So here is an example of that. This was the code that we'd seen before. So how do you fix it? This one is very simple to fix. We can just move it to a range-based for loop. Okay, that totally fixes this problem. But our advice will be, try to move that into a array. That also fixes the problem, but array is better because it's hardened. So a lot of the functions that you have in array are also hardened. So it's better to kind of go to array in this particular case. So that was our array indexing with subscript operator. Let's look at an example with pointer arithmetic. There can be many such examples. I'm just showing one of them over here, and this one will fail to compile and give that error that unsafe pointer arithmetic has been done over here. Again, the fixes will come in various shapes and sizes depending on the type of error. Here, the fix is very simple. Just convert into a string view. Okay, moving on. Let's have this piece of code where we try to actually have an inst array and a length, and then we're trying to print it. So how do you fix it? So as that mentioned that, this code doesn't compile. So you can fix it by converting to a span. So std span, whenever you see a pointer and a size, try to see whether you can convert into a std span. And this reason this actually works fine is that because out-of-bound indexing attempts to a std span will cause a non-exploitable crash in the hardening mode. So with that, let's look at this particular guidance that buffers need to be encapsulated into safe containers and view types. So you have this piece of code over here. So the first one actually just has an int array, and the second one is a const char array. So what should you do? So the first one you should try to convert into a std array, okay, as we have done over here. And the second one, if possible, try to convert into a string view, because string view actually doesn't allocate any memory. And if you have code like this, a function which takes an array and a length, right? Try to convert to a std span. And if you have some code like this, which takes a const caster and a length, then try to convert into a string view. And again, the reason this actually works fine with Unsafe-buffer-usage is that the out-of-bound indexing attempts for containers will cause a non-exploitable crash. Which brings us to the question, what if we cannot fix an Unsafe-buffer problem? So how can that be? Here's some code. So this is a callback coming from a C library. Obviously, we cannot control the C library, so we'll have to actually deal with this particular callback. And if you see this, this will definitely cause this particular problem. So how do you fix it? We saw it before. No, we didn't see it before. Okay, so how do you fix it? So basically, in this particular case, we can just wrap that call, that unsafe code in a hash pragma block, okay? So like this. And once you do that, this code compiles fine. Now, this can be used also in the spans constructor. So let's see how we do that. So here's some piece of code. You can see that there's a span over there, which is what I was supposed to do. We are advising to kind of do that. But what is the problem? So we are getting this callback from unsafe callback, and then we're trying to convert it to a span. And immediately this doesn't compile, okay? Because it says that, hey, the 2-parameter std span construction is unsafe, as it can introduce mismatch between buffer size and bound information, right? So this is one case which is totally applicable to wrap it into that pragma block. And once we do that, this compiles. However, this also introduces a new problem. What is that? So let's look at this. So this code now compiles and works fine because we actually updated mixspan to get it to work. Then I can write this code, which clearly is unsafe, right? Because I'm accessing out of bounds, the array plus 2. This code compiles 2, right? And it gives this garbage output over there. So it would be good to flag all calls to unsafe callback to ensure extra safety is taken while calling them. And we can do that. We can do that using this particular tag. So if you use this tag on a function, it will be tagged as unsafe. And once you have tagged the function as unsafe, if you try to call it, it will fail. Now, there are two options. Either you fix it in some different way, or if you feel that your code is correct, then you can put it in the pragma block. So this additional warning increases the chance of detecting such issues in the coding and the code review phases. Okay, let's move on to the next category, which is C-style functions. So unsafe buffer usage is also flagged for C-style functions like the following, which is a non-exhaustive list. You see the usual suspects over there, memcopy, memset, string copy, etc. The checker is also smart. It doesn't always flag. So if it knows that statically it compiled and there's nothing is wrong, like this piece of code over here, it will not actually flag it. This works fine. There are some more examples available in the LLVM code base. Now let's look at an example with memcopy and how to fix it. So here is us trying to use memcopy over here, trying to copy a string buffer into another. And then since we're using unsafe buffer usage, it immediately gives this error that, hey, memcopy is unsafe. So how do you fix it? You can totally fix it using a span and a ranges copy. So once you use span and ranges copy, this is completely fixed, okay? And let's look at the code output. So this code output is exactly the same. With the memcopy version and the ranges copy version, they have exactly the same output. Now we'll digress a little bit. Because every time I'm amazed to see, okay, what compilers can do, how it can optimize stuff. What am I talking about over here? You see the string hello, right? So whenever you see that hello kind of string, you'll generally see something like this emitted in the code, the ASCII section. But over here, there is nothing like that, right? There is no string over there. Instead, we have this mysterious looking long integer over there, right? What the hell is going on over there? So if you convert the decimal into an hexadecimal, and then if you take the output, convert it into ASCII, you can see that, okay, that hello string is actually hiding over there, okay? It's little linear system. So yeah, that's our wonderful compiler doing stuff for us. Okay, moving on. Let's take an example with memcopy. So this was the code that we had, right? It passes checks and everything. Is it correct? Of course it is not correct. And the reason, because there is no check for the span size over there. So what do? We add checks. So we just move into a new function, memcopy span, and over there the first thing we do is add an assert, saying that whether the destination size is greater than source size, okay? And then we call the ranges copy. And then the code in the main changes to just call that particular memcopy span function. What can that assert be? It can be anything that you want, but for example, it can be something like this, which can be implemented for Clang and x86. What it does is that it puts an UD2 instruction over there. Now again, the compiler is super smart. In this particular case, it can see that statically that, okay, everything is fine. So it just totally removes the UD2 statement and both of them have exactly the same output, okay? Obviously, in the case where it cannot see that, for example, we are actually copying a vector using this approach. And in this case, this is the output that it produces. Don't worry too much about the code, but just see that the UD2 was actually unlikely. So it is moved to the end of the function. And then the usual code actually has a mem move. Okay, so let's take this code again, which was the wrong code kind of, and see what we are doing in Edge and Chromium codebase. So in Edge and Chromium codebase, we have base span, which is an alternate of std span. And that is actually hardened. It has a lot of extra functions, and some of them can handle this memcopy. So what we do is that use one of those functions. We are creating a base span, doing a first, and then doing a copy from. So that is the function that we can actually handle the memcopy over here. Now, if you want to consider the memcopy span, so what we're doing over here is that we are just using that copy from over here. Note, I removed the assert, right? There is no assert of the first statement. And the reason being, that base span copy from will trap at runtime if the source and destination size does not match. And then the main code becomes something like this. Just change the std span with the base span and everything's fine. Okay, enough with memcopy, moving on to memset. So this is me trying to use memset to attempting to actually set all the elements of this array to 1. Let's see whether I succeeded or not, okay? So I'm trying to print something, calling print array, and yeah, of course I did not succeed. So yeah, memset is difficult to kind of use correctly, okay? So with Unsafe buffer, it actually doesn't worry about whether you are using memset correctly or not. It will always flag saying that, hey, it's an unsafe function, right? So what do? So it's very easy to kind of convert this. So basically we can just use ranges fill, and once we do that, we get the right output much easily, and our errors are also gone. Okay, moving on to some statistics from our code base. So Chromium is our upstream code base. So they have reduced the unsafe buffer usage by over 90% in their code base. Is our code, so we know more accurate numbers for that. So for us, actually, the unsafe buffer usage, the non-C library functions, we actually got it down to 0 in 3 months. And then the C library function usage, we are fixed more than 75% in 2 months. Let's round off this section with the state of our code base and what we're doing. So with Libc++ hardening and W unsafe buffer implementation, we believe we are in a good state. It also helps that it's part of the toolchain, so it's harder to kind of miss this kind of issues. Also, we have ASAN in CI pipelines to catch more such issues from tests. Okay, so quick note on what is ASAN. So ASAN is address sanitizer. It's a first memory allocator which can detect out-of-bound access, use after free, double free, and invalid free. Okay, that concludes our section on bound safety. Let's move on to lifetime safety. So this is actually the temporal safety portion. Okay, so this will cover a lot of guidelines and coding guidelines and all those stuff. So the first thing is that, hey, I think we all know this one. Use raw pointers carefully. So let's take examples. So suppose this is another class called another class, and then we have a some class which holds that another class object as a pointer, a raw C++ pointer, right? And then when you do something like this, try to call this do something on that pointer a foo, without careful lifetime considerations, this call can run into use after free. So what do you do? So yeah, this can be totally fixed if you can convert into a unique PTR where the ownership model becomes much, much clearer. So here we have done is that we have actually, in the constructor, we have taken unique PTR as an argument and then replaced that the raw pointer with a unique PTR in the class. This totally solves the issue. However, in some cases, it may not be possible to do that for various reasons. Hence, we come to Chromium raw PTR, also known as miracle PTR, which can be used to handle this kind of scenarios. So the claim is that it can be used to significantly reduce the chances of exploit. So the transformation is very simple. Wherever you're trying to use just a T star, just use a raw PTR T. That's it. That's what you're doing over here. The calling code does not need to change. So the claim is that now this use after free has significantly lesser chances of being exploited under certain conditions. So what are those under certain conditions? So raw PTR depends on certain things. So it first of all depends on the partition allocator in Chromium. Any memorically allocated and freed using partition alloc is poisoned with a particular pattern. So hence this note, it mentions that the sheer act of dereference a dangling pointer won't crash, but poisoning increases the chances that a subsequent usage of the redeemable will crash, giving us a chance to investigate and fix. So it also means that because we depend on partition alloc, it cannot help with literal stack allocated memory, TLS, etc. So the coding guideline that we have in Chromium is that use raw PTR for class and struct fields in place of a raw C-style pointer whenever possible. What about references, right? So similarly, there's a class called raw ref that can be used to handle dangling references allocated using partition alloc. Very simple, right? Instead of another class and we're just using raw ref another class, and that's it. Okay, so raw PTR, what does it do is that it makes the code less exploitable. But safety is not equal to correctness, right? So this does not make it correct. So in our code base, current ownership model and deterministic approaches are always preferred. With that said, let's come back to this piece of code. And suppose you are not able to use a unique PTR. This is like more generic I'm talking about. Consider using WeakPtr. So we just change our class and then instead of taking a raw PTR, we're taking a shared PTR as a constructor argument and we're storing a WeakPtr over there. And then when we call, we're just calling lock, and whenever that pointer is valid, we're calling foo. So this solves that issue. Now suppose there is the case where we cannot even use shared PTR or WeakPtr. What can we do? So one option is that you can store an ID and query it later from another object with a guaranteed longer lifetime. Most programs have such objects. So let's see an example, toy example. I'm creating a class, another class manager, and that has a function called create, which will return objects of another class as pointers. And then there is another function, get with ID. If you pass an ID to that function, it will return that object if it exists or return null pointer. So with this in place, we just make a modification to another class, which just takes in an ID and then stores that ID. And finally, the main modification is in some class. Instead of storing a raw pointer, it's storing an ID over there. So then how does it get the actual value? So when it wants to get that another class, it calls get with ID from the another class manager. And if there's a non-null pointer, then it calls foo. Yeah, this approach may look a little bit contrived, but it really works. We have actually used this in our code base. Okay, so now we talked about shared PTR, right? So we also need to use shared PTR carefully. So for example, assume this particular piece of code over here, assume that it's being used as a shared PTR. Now in this code, we have that function foo, which is calling a fn that is passed as an argument to it, right? We can always run into this output. As you see over here, the my class is destroyed while within the body of the foo function and is called after that, right? So is an use after free. So this kind of things can be easily handled. We can just handle it by using the shared PTR. As you can see that we just increment the strong count over there, and the moment you do that, this becomes the output. So that is a guideline that we may need to increase the reference count of a class before calling functions which may delete that object from when it got called. Let's look at another scenario, which is very common. Async call of member function. So let's see an example. So you have a function called readFile, which takes as a first argument a name, presumably a file name, and then a callback function, which is supposed to call back with the data later. Here is again our my class, which has a new function start reading file that calls readFile, and in the second argument, it passes a lambda, and it captures this argument in the lambda. When the lambda gets called, it will call callback with the argument. In this contraption, it's always possible to get in this scenario. As you can see from the output, the callback can be called after the object had been destroyed. So there are examples in appendix to actually show the entire scenario. How do we fix it? We can easily fix it again by using a shared PTR and a weak PTR. Okay, so we just need to capture the weak PTR in the lambda capture list, and then you can fix it. Okay, so be careful with callbacks being registered for class member functions to be called later, and then consider handling use after free scenarios using WeakPtr or unregistration approaches. Which brings us to the Chromium codebase rules, and this will become a little odd to see. The first thing is that I'm talking about shared PTR and functions, all are banned. Okay? So instead we have replacements. So for shared PTR we have ref counted and ref counted thread safe. For function we have once callback and repeating callback. As the name says, once callback can be called only once, repeating callback can be called multiple times. Now let's take the same example that we saw and see, okay, how do we transform it for Chromium to follow the Chromium coding guidelines, okay? So instead of a function, we just use a once callback over there. And then the calling code needs to change because we have to create that. So base bind once is the way to kind of go and create a once callback. And since this is actually binding a member function pointer, so we need to call it, to also bind in an object to call it. So that's why the second argument is this, right? And the nice thing is that this code does not compile, okay? So immediately we are actually getting out of that problem by default, okay? So we have to compile this, we have to do additional stuff. So here, as you can see, that we have to kind of tag it with unwritten this. So the developer needs to explicitly use base unwritten to get it to compile. Now this change gets us something. It actually gets us safety, okay? The reason being, base unwritten causes the bind ones to store the pointer internally as raw PTR, the one that we saw before, right? So the code becomes safer from use after free exploits. But again, safety is not equals to correctness, right? So usage of base unwritten is totally frowned upon during use, okay? So what we should do is that we cannot use shared PTR and weak PTR, so we have replacement in Chromium. So we actually have a different weak PTR infrastructure that handles this scenario. So essentially, what we do is that we introduce a new member variable called a WeakPtr factory, and then use that to get a WeakPtr, and which is passed as the second argument. Now, this WeakPtr infrastructure ensures that if your original object is destroyed, in this case, my class is destroyed, that callback will never be called. Okay, so that's why we handle this scenario. That's how we handle this scenario. There is another, it's also possible to solve it with something called a base ref counted. I will not cover that. But let's look at one other scenario. Let me try to defeat all this system, right? So bind once can take a lambda. And then I'm doing exactly the same thing. I'm capturing this as the capture variable of the lambda and then calling callback later, right? Which can defeat all this stuff. Luckily, this code doesn't compile. Okay, moving on to our next strategy that we can use, which is to use attributes like Clang lifetime bound. Here is an example of a scenario. So we are having this get.default function, which takes string as the first argument and key as the second argument. And if a string starts with key, it returns the substrings of that particular string. Here is some code calling it. This compiles fine and runs fine. Then I create a new function getString and return a string. In this case, it tries to defeat the small string optimization. It probably doesn't matter, but that's what you're doing. And then we call this piece of code. And here is the output. Clearly, something is wrong. What is wrong? Well, the string being returned by getStr is destroyed over here at the end of the first statement. So when we're trying to access it over here in the second statement, it refers to destroyed memory. So now if you just tag it, if you just tag the first argument type with this annotation Clang lifetime bound, the moment you do that, if you try to call this code, it will give this error. Let's consider one more scenario where Clang lifetime bound comes handy. This is a very commonly used scenario. So we have a my class, which has a string as a member variable. Now string is a heavy type to copy, right? So which is why I have this str function, which returns string as a const string reference. Generally it works fine, but what about this piece of code? It seems to compile and run fine. However, GCC complains, and it complains correctly, because this code is incorrect. Why is it incorrect? So the string being returned by str is destroyed over here. So if I try to access it in the next line, it is referring to destroy memory. So not correct, right? So here also we can use that Clang lifetime bound attribute. And the moment you do that, this code will fail to compile. Now, obviously it's possible to solve this in other ways also using overloading. So for example, here we do is that we actually introduce an overload. So the previous version which returns a const string reference is overloaded only for the const L value. And the other one, we create a new function which is only for the R value. And this works too. One other check that works for us is this dangling, which is enabled by default. Here is some piece of code which is clearly wrong. And this doesn't compile, fortunately, with dangling. Currently, this works only for some STL types. We can get it to work with our different types also with some other attributes. We won't have time to cover those. They are part of the appendix. Okay, this brings us to the end of this particular section on lifetime safety. So let's look at the status, what we're doing. So it's a difficult topic. So we are trying to do various things to handle it. So first of all, raw pointer, it helps with safety. It's actually enforced in the code review phase. There is also checks in the CI pipeline, as we'll see later. Then we have this once callback unreturned WeakPtr. They are partially enforced with tooling, also enforced in the code review phase. Clang lifetime bound currently only enforced in code review. So anything that is in code review is kind of easy to miss. Okay, coding strategy, again, code and implementation review. Dangling good, enabled by default. We also have a few other Clang tidy checks that are used. And then ASAN, MSAN pipelines to help us figure out more such issues from tests. And even after release, we'll cover this later, we actually use GWPAsan. Okay, quickly, a quick note on MSAN. What is that? So that is a memory sanitizer. It's an uninitialized memory detector which can be used to detect mostly uninitialized memory issues. So why did I cover it over here? Because it also covers use after destruction. Okay, moving on to the next section, which will be a much shorter section. This will mostly consist of guidelines, initialization safety. So this is a guideline that we use that initialize members at the point of declaration. What I mean by this is this, that here the member variables are initialized in the body of the constructor. Instead of that, try to do this. Whenever you try to declare that variable, try to see where you can initialize it over there itself. And the moment you do this, it reduces the possibility of making mistakes on missing out on initialization. Fortunately, there is a Clang tidy check that can help us figure out these issues. Second guideline that we use is to kind of initialize properly is to initialize the member initialization list. So for example, this is some code over here. As you can see, this one tries to, in the body of the constructor, it tries to get member B from member A, and then it's initializing member A in the next line, right? So instead, if you just, that code actually compiles fine, okay, and runs in some issues. If you convert in this form, initializing the member variables in the initialization list, then immediately this code runs into a compilation error, okay? It says that, hey, you have reordered it, okay? So the developer looks at that and then reorders it correctly based on the order of initialization actually, and then this code works fine. Finally, we also ask developers to initialize variables. So if you have something like this, don't do something like this, just use int a equals to foo, okay? Fortunately, there is also a Clang tidy check that can help detect such issues. Also, making variables const can help compiler detect such issues. So if you have something like this, the compiler will automatically complain. Now, Clang tidy also has a various number of other checks which check for uninitialized variables in various scenarios. So consider using those. We actually use those in our CI pipelines. Fortunately, C++26 comes with P2796, which removes the undefined behavior with uninitialized variables for certain scenarios. That brings us to the end of this section. Let's see what we do in Edge. So we use coding guidelines, code review, warning flags, Clang tidy checks, and also MSAN pipelines to figure out more issues with tests in CI pipeline. Okay, handing off to Bharat for the next section.
Thanks, Chandra. Let's take a look at how to reduce type confusion. Our guidance is to avoid type punning. What's type punning? Type punning in C++ is essentially the practice of reinterpreting the memory representation of object of one type into another type. Here's an attempt to type pun int into float. Here's a union. It has int and a float member. And in this function, we are trying to initialize it with an integer and try to return it as a float. And here's the function as a const x for float f being initialized by calling this function. So this will fail with a compiler error saying that, okay, you cannot do that. This code is correct in C, but in C++, it's an undefined behavior. So what's our recommendation? The guidance is to use bistcast, which works correctly in this scenario, and instead of using the union hack for these kind of scenarios. And also, rather than reinterpret cast, our guidance is to use bistcast as well. Let's take a look at reinterpret cast. In this particular example, in the get float, we have a cat star p, and we are trying to reinterpret it as a float star. Now, this can fail on some platforms and run into a SIG-bus issue. Why? Because some platforms like ARM, they have a very strict memory alignment requirements. And on Intel, it can run into issues with the SIMD code. GCC has a wcast-align strict flag for this kind of issues. Now, how do we fix this? One option is to use memcopy, and the issue is resolved. But with memcopy, we can run into the unsafe buffer usage problems, and our guidance is to use some kind of wrappers. In the Chromium library, we have these kind of wrappers available. Clang tidy also has these checks, which can flag all these reinterpret cast or static cast issues. The problem is it will flag all the uses, including the valid ones as well. And we also have the sanitizer for the addresses, which can potentially create the runtime errors for such unaligned access issues. Now, next guidance is to use variant in place of union. Here's a code which uses union in an incorrect way. We have a wrapper class which has a union, and we are creating a wrapper object here which can crash at runtime. Why? So the constructor here is not initializing any of the member variables correctly. And as a result, the destructor is also not working correctly. And if we look at the set functions, it's not even calling the destructors or the previous types at all. How can we fix this? We use variant, which have with a string and a vector integer, and this code works correctly. We also have control flow CFI, control flow integrity, which can help find these kind of invalid cast issues. Here is an example. We have a base class, which has a function foo, and then we have a drive class, which also has the override for the function foo. In the main, we are trying to create a object B of type base, and then we are trying to cast it into a derived class D. If we have the CFI enabled, then at runtime it will crash saying that, okay, you are trying to cast from base to derived, and the V table is wrong here. What's our status here? So we have the coding guidelines to catch these kind of issues, and during code review, we try to catch some problems. And also we have the CFI enabled in our CI pipelines. Now, moving on to the thread safety. So how do we avoid the thread safety issues like deadlock and race condition? So we use sequences in our code base. And sequences are essentially Chromium abstractions on top of our system threads. We have internal libraries for supporting all the different sequences. The code can create its own sequence and post a task to any sequence. You can post to any task or a specific thread, like UI thread or an IO thread. And the library takes care of all the synchronization for all the sequences. The guarantee is that the task posted to a sequence will run in the same order as they were posted in. And even though each task can run on in a same sequence can run on different physical thread, the library ensures that there is synchronization and the tasks are running in the same sequence. Very useful utility is that you can post a task on one sequence and get the result and post a task with that result on another thread as well. Here's an example. So we have a scenario where we want to read some items from the disk on a background thread. And then we want to perform some task, use some items in the UI thread. It's possible to do that with the sequence. So we have this post task and reply with result. It's asking to post this task on a background thread, and with the result, call back the UI function. How it works is, so we have the UI thread, it will post the task on the background thread, it performs the task, and then with the result, it will call back the use some items in the UX on the UI thread. And that way the sequence is ensured. How do we ensure it in Edge? We have the coding guidelines, and we try to catch some of these issues during the code reviews. We also use thread sanitizer in our CI pipelines, which is essentially a data race detector. With that, handing over to Chandra for the definition safety.
Thank you, Bharat. Let's moving on to the next section, definition safety. This will also be a small section. So we start with ODR violations. So this comes under, so ODR is one definition rule. This comes under IFNDR, which is ill-formed, no diagnostic required in C++. So here is one simple example. So just a concept of variable in a header can cause ODR violations. It's possible to do that. So fix is very simple, just make it in line. So it ensures that the one definition rule is not violated. Also ensure preprocessor flags are used consistently. This is a tricky thing to do. Let's see an example. Okay, so we have this my class which has this macro special source. And when the special source is present, there's a special function and there is a special number, which is a member variable. Okay, we have this myclass.cc where I'm defining that particular macro. So in an actual case, it will come from some kind of a build definition file. Here I'm just showing it as an example. And in main.cc, I don't have that macro. And here's the code. I'm just calling myclass, creating myclass object, and then calling str. Now this code can totally terminate at runtime. And this is based on a real life example that we saw in your code base, which is caught by an address sanitizer. Okay, what is happening over here? Let's look at this. Okay, so this was the code of my class. This was the main that called it. And this is my class constructor, only the portion that causes problems, okay? So as you know that my class is saying only this much. Sorry, main.cc is saying my class only this much as a std string. My class.cc is saying more of my class, okay? But the code starts at main. So, and then considering std string is 24 bytes, in main.cc, that string underscore variable is placed over here, 24 bytes over there. Then my class, which is in the my class constructor definition, the str actually is placed like this. As you can see, it's already trying to do something out of bounds. Okay, so now this code runs, which is calling the move constructor of std string, and this comes and overrides over here. So this is small string optimization happening. And so immediately we can see that there is an out of bounds, right? And then we do this hash and it goes and overwrites over there, okay? And then main.cc interprets this portion as a string and hence it crashes. Okay, one more simple approach for ODR violation fixes is if you have something like this, which is a source or CC file, which has a class, a global variable and a function defined only for the source. In this case, we'll suggest that move it into an undefined space, okay? So that becomes the guidance. Add any source only classes, variables, and functions to unnamed namespace to get internal linkage, hence remove the ODR. Which brings us to the end of this particular section. Let's look at what we do to improve definition safety in Edge. So use coding guidelines, code review, and of course, use ASAN runs in CI pipeline. Moving on to the next section, reducing undefined behavior. So there's a lot of undefined behavior in C++. Let's see what are some of the strategies that we use. So first guideline is that try to use const expr, const int, and const variables. So here is some code. So this code runs into a signed integer overload because we're trying to add 1 to int max, right? But this compiles and runs and gives that error at runtime, right? The value is incorrect. So the moment we move it into a const expr, the moment you do that, the compiler gives an error. Even const, if you just make it const, that will be an error too. So which becomes a guideline that consider making variables which can be calculated at compile time const expr or const that will help catch undefined behavior. One more quick example, division by 0, modulo by 0, and shift operation, this shifting by -1. All these are undefined behavior. And this code compiles just fine, okay? So just make them const. And once you do that, no compilation, there's a compilation error, okay? And these warnings are enabled by default. One more strategy to reduce undefined behavior is guideline is that consider using const expr and constable functions when applicable to detect undefined behavior. We have seen this used before when we saw this type panning getting caught, this particular example. There is a wonderful article by Shafiq Yaghmour which mentions many such more examples. Now, undefined behavior can cause unwanted optimizations also, like this very interesting scenario which comes from 2011 LLVM blog. So this is some code. So we have a fp, which is a function pointer which is set to null, 0, and then an impl function which does a print. There's a set function which sets impl to fp, and there's a call which calls fp and main calls call. If you can look at this, look at the code, then set is never called, so this code should crash, right? But when built with Clang with -02, this gives an output hello. This was never called, right? So here's the assembly. As you can see that the set is just a ret. The body is completely removed and the main directly makes a call. So why does it do that? Because it's allowed to do so. Because calling a null pointer is undefined, so it permits it to assume that set must have been called before call. It can do that. So when built with this particular check, no delete null pointer checks, then this terminates because the code behaves like that, so it removes that optimization. Okay. Looking at the documentation, it mentions that this particular check is on by default, and when it's on by default, then treat null pointer difference, creation of a reference to null as undefined behavior, and optimize our branches accordingly. Our codebase has this one, so which removes this particular undefined behavior. Let's consider one more undefined behavior, which is missing return in function. Luckily, this one is also caught by Clang. This W return type is a default one in Clang, and it also catches it. And as the standard mentioned, that this is also undefined behavior. One more tool that we use to handle undefined behavior is sanitizers. This happens only at runtime. So the Clang actually has a multiple undefined behavior sanitizer checks, and we use those. So let's close out this section to see what we are doing in Edge to reduce undefined behavior. We employ a variety of tools, coding guidelines, code review, Clang tidy checks, and also undefined behavior sanitizer runs in CI pipeline. Okay, handing it off to Bharat for the next section.
Thanks, Chandra. So as I mentioned, during the implementation phase, we invest a lot in writing the fuzzers. For the fuzzers, we mostly rely on libfuzzer, which is essentially our coverage-guided fuzzing engine. It's very easy to reproduce the crashes with the engine, and it also integrates well with the sanitizers. Here's an example which uses the fuzz data provider. We have a function process which we want to fuzz. So we have the fuzz data provider which provides us with 2 random integers, and we are able to call the same function in a loop in a fuzzer. Given that we are a browser team, we need some advanced fuzzer than libfuzzer. So we have the Domato and Fuzzly that we use. Domato is the grammar-based generative DOM fuzzer, which helps us fuzz HTML, CSS, and JS samples in our DOM engine. And the Fuzzly is for V8 engine. It's very efficient for finding the JIT and the type confusion bugs, and it also uses REPL for very fast execution. In terms of statistics, with our fuzzers, we run them with add-in sanitizers. So we identify nearly 700 crashes, and 200 plus of them were security bugs. It excludes any external bugs which we report to the Chromium and duplicates. Moving on to the code review and the CI pipeline and after release process. So during the code review, our reviewers run against a possible checklist of all the issues. We also have pre-existing rules for our bots which can put a comment on the PR. We try to use AI to assist with some of these code reviews. And for the security sensitive files, we ensure that the security reviewer is always reviewing that particular code. In our CI pipeline, we have multiple stages. Some of them are pre-submit checks, Clang plugins running the Clang tidy, static analyzers, and sanitizers, which we'll take a dive into. So how does our pre-submit checks look like? So we try to catch the uses of unsafe APIs in this phase. For example, using chrome.send or memcopy, or trying to use any unsafe crypto libraries. We also ensure that the security reviewers are present in the code review and try to scan for any passwords or secret keys being added by mistake in the PR. Looking at the Clang plugins, these are additional plugins which can catch issues during the build phase. So we use find bad constructs, which essentially identifies any missing virtual keywords on the methods which should be virtual. And it flags that any class that derives from base ref counted or the ref counted thread safe, it should either have a protected or a private destructor. Another plugin we use is the raw PTR check, which helps ensure that we are using miracle pointers correctly. It ensures that any class data members are declared as miracle pointer rather than a T star. And it increases uses of raw reference, raw underscore ref T rather than using the raw references. And it flags any unsafe cast, like reinterpret cast or static cast, because it just defeats the purpose of using a miracle pointer. And it also disallows using miracle pointer for a stack allocated type, because in that scenario, the use is unsafe. We also have Clang tidy checks. Here are some of those checks that we run in our CI pipeline. Then we invest in static analyzers. We mostly use Waggly queries for our static analysis because it's very lightweight compared to something like CodeQL, which relies on a database. It works on Clang's AST, and it's very useful for finding some of the low-hanging fruit. In this example, we have a function getName, which tries to return a pointer to a character array underneath a string, which is already being destroyed at return. And here's a simple Waggly query, which can identify all these patterns across the whole code base. Moving on to the sanitizers, so we run ASAN, MSAN, and UBSAN pipelines periodically through our tests. and it helps finding all the memory issues. Here's an example of a classic use after free. So we have a pointer, we are freeing it, and then you're trying to use it again. So ASAN will flag it for us. And same if we have a uninitialized variable, in this case x, we are trying to use x even if it is even when it's not initialized properly. So the MSAN will catch these kind of issues for us. And in case of UBSAN, we have a scenario where we are trying to add A and B, and there's a potential of having a signed integer overflow. So the UBSAN will flag these issues for us. Now, moving on to the after release phase, we use GWPAsan to catch any issues in the wild. It's a simple sampling-based memory error detector which can identify use after freeze, heap buffer overflows, or double freeze in the production environments with very minimal overhead. How it works, so it uses a sampling allocator, so it randomly selects a small fraction of heap allocation to place in a guarded pool. And it also uses guarded pages to identify any overflows or underflows surrounding the selected allocations. It has a concept of delayed freeze. So if any memory is deallocated, it will quarantine that memory so that it can detect any use after freeze. And in case of any illegal access, it will trigger a segmentation fault. We receive that dump, which helps us enable with the debugging. In terms of stats, we were able to have 1,200 crashes reported to us using GWPAsan, and we fixed almost 140 security bugs which were identified. So what's the conclusion? So the building secure C++ application requires a multi-layered approach. There is no silver bullet. And incremental improvements are possible by adopting the safer coding practices or by leveraging modern tool chains like C++20, Clang, Libc with hardening, Unsafe-buffer-usage, or Clang tidy checks. By using compile time and runtime checks, or using sanitizers and fuzzers in our environments. And we should also try to focus on core safety categories like lifetime bounds, initialization, and type safety, along with thread and definition safety. We should try to integrate security reviews, static analysis, and sanitizers throughout the development life cycles from design to release. Most of the codes that we used in this presentation and additional ones are present on GitHub, and we have some of these code snippets also available in the appendix. And we hope this talk gives you something interesting which you can use in your code in the future. And a big thank you to the Chromium developer team and our awesome Edge development team. Also, especially to Kathleen and Prithvi for helping review the content of this presentation, and the wonderful C++ community for the books, blogs, videos, questions, and answers. There is a big presence of Microsoft colleagues at CppCon. We have multiple of these talks. Our talk is the first one here. And there is also a survey to get feedback. So you can use this QR code to give the feedback. And there is also a raffle to win the prizes. So any questions?
My question is about Bitcast. Are there any cases where both would work and you still do prefer interpret cast? And in particular, how do you deal with casting between unrelated pointer types?
Yeah, I think Bitcast would actually work. My understanding is that there are some things you cannot do with Bitcast. For example, unrelated pointer types casting, you shouldn't do with Bitcast. So it's only certain types of things, the ones that work with memcopy, those are the ones that should be used.
So we are not with Bitcast, although you can.
You can
probably work.
Yeah, but it will actually give undefined behavior. Mm-hmm. Thank you.
So you mentioned that you integrate AI into your code review process. How useful did you find it? Like, how is the noise versus actual useful command ratio?
So it's still in the early phase. So the noise ratio is a bit higher than we would want it to be, and we are trying to improve it as we go along, and bring it to an acceptable level. Yep. Yeah. So it's still in the early phase. That's what I would say. Yep.
Yeah, I'd say 50-50. It's quite high.
I see. Can the AI actually understand the code and point out very complicated error in scenario, like just like very obvious ones that it can point out?
Yeah, sometimes it does point out obvious ones, and even non-obvious ones it does point out.
I see.
Yeah.
So with the AI, the effectiveness is essentially around your context window. it can help identify any issues. If you have written a new function, it will point it out for you. But if you are expecting that, okay, it can trace all your data flow across the whole project, then that's, that's a big ask. You can potentially do it with AI, but, you will probably have to run a lot of, code in your clusters maybe just to identify that one particular issue. So,
I see. Thank you.
Thank you. Yeah, thanks for the talk. So on a lot of these, you were pointing out that for your sanitizers, you enforce them by running them in your pipelines. What exactly are you running in your pipelines? You're building with the sanitizers, but
yes,
what are you building and what do you do with it?
We are running our tests, test binaries with sanitizer instrumentation, so they can identify any issue. So any code which is covered through our test, we're
Right.
able to identify all the issues.
So you're building the actual executable and running it on a canned set of test data? Or you're running your unit tests?
So we have the set of unit tests, browser tests, like the comprehensive test suite,
Okay.
which runs with all the sanitizers. We have something additional as well, but it's
Okay. So mainly the unit tests. Did I hear that right?
Like in the CI pipeline, it's the unit test as well as like we call them browser tests. Like it's more of
Okay.
like a comprehensive set of tests.
So
not
you've
just
got a set of inputs or a set of whatever that you feed into it.
Correct.
In a
correct,
sense.
correct.
Okay.
So for us, actually, the unit test is actually a non-integration test. The browser test behaves more like an integration test.
Okay.
There is something like an interactive UI test also, which can actually click on stuff. So
Okay,
all those actually run with sanitizers. And finally, the release build actually goes out and then runs with GWPAsan. That is actually for a general scenario. Like if any user is just using it, that will be catching it.
Good. All right. Thank you.
Welcome. Any more questions, comments? Okay then, thank you all. Have a nice rest of your evening.